Welcome to the deep dive. Today we're tackling a huge global issue, fresh water, or rather the lack of it.
It's a challenge that just keeps growing, isn't it? Finding enough clean water.
Exactly. And while desalination isn't new, we're zooming in on a specific technology today, reverse osmosis, or RO. It's really changing the game.
It absolutely is. The demand for potable water is just immense, and RO is proving to be a vital solution for, well, millions of people.
Right. And we've been looking through this detailed brochure from ENGIE. They're a major player in this space, focusing on sustainable solutions.
Yeah, they are leaders in this field.
So our mission today is to sort of unpack the science behind RO, get into why it's so beneficial, and see how it's actually being used, on a massive scale to deliver water reliably.
It's a fascinating intersection of science, engineering, and frankly, urgent human need. The impact is quite something.
Okay, so let's start with the basics, just to make sure everyone's on the same page. Desalination, what is it fundamentally? And why is reverse osmosis the key technology now?
Right, so desalination at its heart is just taking the salt and other minerals out of seawater, or maybe brackish water, to make it drinkable, or usable for farms or industry.
Simple concept, complex process.
Very. Now, the big shift with reverse osmosis compared to older methods that basically boiled the water is that RO uses pressure, a lot of pressure.
Okay, pressure, not heat.
Exactly. You're forcing water through a very, very fine membrane. Think of it like a molecular sieve. Water molecules get through. Salt ions, minerals, other impurities. They don't.
Ah, so it filters at a tiny scale.
Precisely. And because it relies on pressure, not boiling vast amounts of water, it uses significantly less energy. That's a key advantage.
Less energy, that's huge. I mean, energy costs are always a factor. What else makes RO stand out? Are there other big benefits?
Oh, definitely. That energy efficiency is critical, like you said. It makes desalination feasible in more places, lowers running costs. But also, RO membranes are incredibly good at removing contaminants.
Like what kind of contaminants? Just salt.
No, much more than salt. We're talking heavy metals, minerals, and even things like bacteria and viruses. It's very thorough.
Wow.
So the water quality you get is consistently very high, often purer than what you might get from traditional sources.
So reliable quality, not just quantity. That must be important for health, for industry.
Absolutely crucial. And tying back to the energy point, less energy usually means a smaller environmental footprint, right?
Yeah.
Lower carbon emissions compared to those older thermal plants.
Makes sense. Better for the planet, too.
Yeah. And another thing, maybe less obvious, is operational flexibility. Our plants can be started up and shut down much quicker than thermal ones.
Why does that matter?
Well, it helps manage fluctuating water needs, and it's also really useful if you're integrating with renewable energy sources like solar or wind, which can be intermittent. That agility adds another layer of water security.
Okay, so it's efficient, effective, cleaner, and flexible. I can see why it's become the go-to. Now let's get into the nitty-gritty. How does it actually work? Walk us through the process, step by step.
Okay, let's follow a drop of seawater. It starts, naturally, with seawater intake. This involves large structures, usually offshore, pulling water in.
Just sucking it straight in.
Well, yes, but with screens and barriers to keep out fish, seaweed, big debris. You have to protect the equipment downstream.
Right.
And often, right at this stage, there's a bit of early treatment. Things like coagulation and flocculation tanks. They use chemicals to make smaller particles clump together filaments, tiny organisms so they're easier to remove later.
Sort of a pre-cleaning step.
Exactly. Preparing the water for the really fine filtering. Which brings us to step 2. Pre-treatment.
More cleaning.
Yep, this is more intensive filtration. The water goes through various screens that may be sand and gravel filters. The goal is to remove suspended solids.
Stuff floating in the water.
Right. And also, critically, you need to prevent biological growth microbes, algae that could clog up the membranes later. So often there's chlorination or some other disinfection method used here.
Like treating pool water.
A bit like that, yeah. And then usually there's a final pass through cartridge filters, like really fine physical filters, to catch anything left before the high-pressure stage. It's all about protecting those delicate, expensive RO membranes.
Sounds thorough. Okay, so the water's been screened, clumped, filtered, disinfected. Now what?
Now comes the power. Step 3, high-pressure pumping. Special RO feed pumps take this pre-treated water and dramatically ramp up the pressure.
How high are we talking?
Very high. Enough pressure to overcome the natural osmotic pressure and force water through the membranes. This is where a lot of the energy goes.
Okay, makes sense. And that leads us to the core of it all.
Exactly. Step 4, the RO process itself. The high-pressure water now flows into modules containing the semi-permeable membranes. These are often spiral-wound sheets packed into long tubes.
And this is where the magic happens.
This is it. Under that intense pressure, water molecules are forced through the membrane's microscopic pores. But the dissolved salts, minerals, bacteria below, basically everything else gets rejected, left behind.
So water goes through, salt stays back.
That's the essence of it. You end up with two streams coming out. The pure fresh water, which we call permeate, and a stream of highly concentrated salty water called brine.
Permeate and brine. Got it. So is the permeate ready to drink now?
Almost. That's step 5, post-treatment. The permeate water is actually too pure sometimes. It can be slightly acidic or tasteless.
Too pure. How?
Well, it lacks the minerals that give water its typical taste and stability. So in post-treatment, they adjust the pH, often add back small amounts of minerals like calcium and magnesium. This is called remineralization.
To make it taste better and less corrosive for pipes, I guess.
Exactly. And there's usually a final disinfection step, just
Uh-huh.
to be absolutely sure it's safe before it goes into the distribution system, making sure it meets all drinking water standards.
Okay, final polish.
Then, the final step, step 6, storage tanks. The finished desalinated water is stored in large tanks. This ensures there's a buffer, a steady supply available for the community or industry, smoothing out any variations in production or demand.
Providing that reliable flow we need. Wow, okay. That 6-step journey, intake to storage, it really paints a picture. It's quite an
It
operation.
really is. A lot of sophisticated engineering involved.
So let's connect this back to the real world. We mentioned ENGIE. They're clearly a big force in this area, especially focusing on sustainability, aiming for net zero by 2045. That's ambitious.
It is ambitious, and
Mm.
their approach seems quite holistic. It's not just using RO, but powering it sustainably. They talk a lot about integrating renewable energy solar, wind right at the desalination plants.
So decarbonizing the energy supply for the water.
Right. Plus, they're constantly working on making the processes themselves use less power and just running the plants really efficiently. It's about the whole life cycle.
And they've been doing this for a while, right? The brochure mentions over 30 years working in the Middle East, helping countries with their low-carbon goals and water needs.
Yeah, that long-term experience is definitely a factor. They have deep expertise, especially in these complex projects where you decouple power generation from water production, these independent water projects or IWPs. They were early adopters of RO technology too.
That experience must count for a lot. And the scale they operate at, it seems huge.
It really is. The numbers are quite staggering. Globally, they have 19 desalination plants running, 4 more RO plants being built, and specifically in the Middle East, they operate 15 RO plants.
15 in just one region. What does that translate to in terms of actual water produced? How many people does that help?
Okay, so across their plants in Asia, the Middle East, and Africa, what they call the AMEA region, the total daily production capacity is around 7.3 million cubic meters.
7.3 million cubic meters every day.
Every day. And at full tilt, that's enough potable water for over 10.6 million people daily.
Wow. That's
them-
more than the population of quite a few countries. Providing clean water on that scale every single day, that's genuinely impactful.
It's fundamental. It underpins health, economic activity, quality of life. It's hard to overstate the importance.
Can you give us a couple of specific examples? Where are some of these large-scale plants?
Sure. Let's see. In Bahrain, there's Azor North. That one produces 107 million imperial gallons per day of EGD. ENGIE has a stake in that.
107 AMD. Okay.
Then in the UAE, Shuihat 1 is another big one, 100 MEGD. And in Saudi Arabia, Jebel 3B is even larger, 125 MEGD. ENGIE has significant ownership stakes in these too. These are massive industrial facilities.
Those numbers really drive home the scale. It's not just theoretical. And it sounds like ENGIE isn't just running existing plants, but pushing the technology forward.
That seems to be a key part of their strategy. They launched something called the Desalination Center of Excellence, the DTOE, back in 2023.
A center of excellence, what's the focus there?
It's about innovation. They're working with partners on several fronts, making existing plants even more energy efficient, exploring completely new types of membranes. And this is really interesting, looking at ways to revalorize the brine.
Revalorize the brine. You mean the salty wastewater?
Exactly. Instead of just disposing of it, which can have environmental impacts, they're looking for ways to extract valuable minerals or find other uses for it, turning a waste stream into a resource.
That sounds like a potential game changer. Closing the loop, almost.
It could be. It addresses one of the main environmental concerns with desalination and could even create new economic value. It's about improving the overall sustainability profile.
And this kind of long-term thinking, this innovation, it fits into broader national plans too, I imagine.
Absolutely. The brochure highlights how ENGIE's work aligns with things like the UAE's Water Security Strategy 2036 and Saudi Arabia's National Water Strategy. They're positioning themselves as partners in achieving these big national goals for water resilience and sustainable development.
Well, this has been incredibly enlightening. We've really gone deep into reverse osmosis, what it is, how that step-by-step process works from intake right through to storage.
It's a complex but elegant process when you break it down.
Yeah, and seeing the sheer scale of it through examples like ENGIE's work, it makes it clear how vital this technology is for delivering clean, reliable water to literally millions of people. It's not just an abstract concept, it's happening now on a massive scale.
It really is a powerful example of applying science and engineering to solve a fundamental global challenge. And seeing the scale and the ongoing innovation, it does give you a sense of, well, cautious optimism about water security for the future.
Definitely. So as we wrap up, here's something to think about. As this technology keeps evolving, especially with ideas like revalorizing brine, making it even more resource efficient, and cutting the energy needs further, what new possibilities could open up? Could it go beyond just solving water scarcity to actually creating new economic opportunities or ecological benefits, particularly in arid regions?
That's the exciting frontier, isn't it? How far can we push this technology not just to provide water, but to do it in a way that's truly sustainable and maybe even regenerative?
Something for all of us to ponder. Thanks for joining us on this deep dive.